All right, our next presenter is Stig Telfer from StackHPC, where he's CTO. Stig, welcome. Thank you for joining us.
Thank you for having me. So I'll just get my things set up here. Has it come through okay?
Yes.
Okay, great. So that's a huge act to follow, both of this afternoon's sessions. So I hope to build on it, but I have a slightly different focus in terms of the content and what we're talking about. We're going to be building on operating and making our own clouds for software-defined HPC. And to back that up, I've got a little example which is aiming to showcase why it's worth the trouble. In my career, I've worked in some amazing places, and I was just thinking about what Gilad was saying, because early in my career, I was working on GPU offloads, and towards the middle, I was working on software-defined NICs for MPI, and it's just amazing to see how these things are now coming to a very productive fruition. I think you won't have heard of our company. I work for a company called StackHPC. You won't have heard of us unless you work in the niche of HPC on OpenStack environments, particularly. We're a small consultancy based in the UK, dwarfed by a tremendous fortune to have gathered together within the company a team with a really sort of global reputation in open source and scientific cloud as well. So for this talk today, I was going to talk a little bit about this idea of the software-defined supercomputer, but mostly I wanted to cut to the chase and share with you a little podded case study of how we use this software-defined methodologies to good effect. And in that case, we're looking at a analysis of high-performance storage in a cloud-native context. So hopefully I'll be able to tease out a good angle for today's content, and hopefully it'll be interesting to you. So I guess we should start by laying a couple of foundational concepts. I'm sure people have already heard about this sort of software-defined supercomputer. It's totally buzzword compliant these days. All kinds of vendors in HPC are talking about cloud-native interfaces. It's an idea whose time has really come. So people already provide cloud computing services for HPC and AI. So what is the big deal with cloud, and why should it change things? Well, I think actually the biggest deal is not actually cloud. It's the mindset, the DevOps mindset and skill set, and the way that can affect organizations, HPC service providers like Cambridge, for example, and how those organizations and the people within the team, the people at the top of the stack, if you will, how they can become a high-performing team operating with these truly complex, truly vast exascale infrastructures. So the way that cloud thinks about it, there's interesting things. I mean, they look at how you measure what makes a team into a high-performing team. For example, they look at how we can deliver on our performance. So how to measure that? So we measure how long does it take your team between you asking for something or your users asking for a feature to that feature becoming part of the production system. They might say, well, everything's gone wrong, something's failed. How quickly can we restore things when everything goes south? And then, of course, we can say, well, how often when we try to make a change to our environment, does that change work? And how often does it go wrong and need fixing or backing out eventually? And finally, how quickly can we make changes? So fundamentally, to work in a software-defined environment, it's about working without fear of making changes. So all of the technology, all of the automation, all of these extra pieces of effort are applied simply to take away the risk of making a difference. And that actually feeds into all the other pieces here in terms of how we actually run a high standard service, a highly available service for our users in a way that is produced by a high-performing team. Software-defined supercomputer, and it's also covering a wide range of other concepts. This idea of consolidating a broad range of siloed platforms, an HPC platform, a big data platform, perhaps an AI platform as well, and putting those siloed platforms into one converged substrate is really what the tech companies are advocating. So we put software-defined APIs in front of this thing, and that gives it a cloud-native feel, upon which then we can build a diverse range of user platforms, application stacks, and so on. And for us, this deployment of a rapidly reconfigurable platform is the key enabler. The interesting piece, though, I think, is when you bring together this consolidation of resources, it doesn't mean that you're providing one size fits all to your users. Absolutely not. So we can provide these interesting ideas around how things like APIs can give us flexibility. We can ask for a network. We can ask for a storage resource. We can bring these things into our applications and our platforms in ways that we simply wouldn't have been able to do it, certainly not in a timely way previously. One of the key enablers that has happened in the last maybe 2 or 3 years has been the ability to mix together in a really exciting way a component of bare metal compute and a component of virtualized compute. And then actually over recent cycles to sort of dissolve away the borders between the two, so that our virtualized environment is simply a bare metal node that's running a workload that happens to virtualize it. This is really transformative power. It means that when we make a software-defined supercomputer, we can build something which has no overhead, none at all, where we need it. And it has no inconvenience in terms of working with software-defined infrastructure where we want that too. So we get rapid cycles, quick spinning, high utilization of a system where we need, and then complete performance, nothing sacrificed where that matters too. And this has been really the game changer from our point of view. The interesting way of doing this is that we can bring about these concepts. In StackHPC, we've got two of them we call generalized specialization. Is the idea that we can take our hardware and we can adjust it. We can tune the BIOSes. We can change the way the storage is working. We can do all kinds of interesting things with the networking in service of what kind of workload we want to run. And taking that to the fullest extent possible, this idea of hardware polymorphism is where we start to look at changing parameters within the firmware. Let's say we want to run Hadoop on the node one day, we want to run an HPC workload on the node the next day. Being able to reconfigure a generalized piece of hardware resource as far as we possibly can at the firmware level, simply by the user asking to boot a machine of one flavor or another. These are really powerful concepts. And this is, I think, what really brings this idea of a software-defined supercomputer from being just like a bunch of nodes in like a little snow globe environment to being something which you can actually use in production and to good effect. So those are the key enablers for us. And I think that's probably enough to cover about that. So what did I want to talk about today? There's been a strong theme around Exascale and the Excalibur program in this workshop. And so I wanted to pick a topic which sort of might be interesting from those pieces. So here's a case study which we recently did around evaluating the performance of file systems in an Exascale context. You read the tea leaves and you see which way the wind's blowing, and it does appear that the idea of a single giant POSIX namespace, a single file system mapping all of our infrastructure, is not scaling as well as the amount of compute capacity that we're piling into mounted as clients. So things are there are cracks at the edge of this idea, and it's starting to change. I think object storage has possibly got a role to play here, but it doesn't appear that it's going to have a completely sweeping transformation of the whole thing. So this idea about dynamic file systems, something that Paul was talking about earlier, is quite an interesting piece to bring in here. We bring in a high performance all flash tier. It runs, it exists, it's created in service of a job. When it comes to the front of the queue, it runs, and then the data is drained away in a way back to a production storage. And the idea here is quite an interesting one, but it's also not exactly how these file systems were written in the first place. And I think a wise person once told me it takes 10 years to make a parallel file system and to make one which you trust with production. So they're being used in a way that they simply haven't been evolved to cope with. So you've got to wonder, how do you test them in this kind of environment where we are using a parallel file system as a flash tier? We make it, we use it, bang, and then it's gone. How do we actually evaluate this new way of doing things? And so with these challenges, we've got an opportunity to evaluate them in a nice sort of cloud native testbed, because it provides these kinds of foundations for rapid prototyping in a high performance environment. So at StackHPC, somewhat predictably, we use OpenStack to construct a high performance cloud environment and do it on solid foundations. If you're ever looking for a metaphor for solid foundations, I believe this is a Silk Road fort in Bukhara in Uzbekistan. I've never actually been there. I'd love to be there. But anyway, so using the cloud native testbed provides a nice level playing field for us to do prototyping and explorations. And the cloud native components of it also provide a nice clubhouse to go with that level playing field. So that is how we attack these things. And this is how we generate rapidly prototyped systems. Does cloud native mean virtualized though? I think we've already answered that question a little bit, but it is a question which is continually getting revisited and reevaluated in an ever-changing context. One of the historical problems with virtualization has been getting any kind of performance from virtualized networking. And if I told you that this is a diagram of all of the software network interfaces in a hypervisor that's simply running a couple of VMs, you could probably get a feeling for why. I mean, software-defined networking is based on a rich set of what we call flow rules. And flow rules are implemented using this fairly complex chain of bridges and software-defined switches. The big three green blobs in the corner of this diagram are what's called Open vSwitch. So these are open flow programmable network switches, and they are implementing the bulk of what software-defined networking provides. So firewall rules, tenant network separations, routing, and so on. When these are implemented in software, as depicted here, it is true that they can be truly painful. And so virtualized networking has historically been a non-starter for any of the kind of MPI workloads that DK was talking about just now, unless you throw some sophisticated hardware into the mixture. So this is the other piece of transformation that's happened in the last couple of years, or last few years. The graph here actually is from a presentation I did with in collaboration with Erez Cohen from Mellanox in 2017. What we're looking at here is 100 gig Ethernet and an all-to-all exchange between 4 VMs that were not co-resident, so on separate hypervisors, internode exchanges. And we were lucky to prototype this on several different clouds and also several different strategies for software networking. And what we brought together was bare metal Infiniband and hardware offloaded Ethernet networking, and then all of the kind of software networking that we were looking at here as well. And it's hard to get the performance of these different strategies onto one graph, so it's a log scale. And so we see that we really can't do all-to-all exchanges, this kind of pathologically worst case exchanges scenarios in a software-defined networking environment unless we do some kind of hardware acceleration. Usually in virtualized context, that means bringing in this technology called SRIOV. Now, SRIOV gives us about sort of 0.2 microseconds of latency on top of what you get in the bare metal context, which for most cases is perfectly adequate. But it does also compromise in fairly significant ways the kind of work that we can do in a sort of with all the cloud native convenience. Now, recently that has all changed. So in the release of OpenStack from about a year and a half ago, we gained the ability to apply live migration to our systems. And with the Mellanox's recent introduction of hardware offloading for Open vSwitch flow rules, we can also do things like security and firewall rules on the silicon themselves using this thing called ASAP squared. The final piece is that when you have a cloud system, usually it's configured for very strong fault tolerance. So a lot of the components within the system are dual redundant. And an SRIOV virtual function maps to a physical device within the hypervisor. If that fails, then your virtual function fails and all of the VMs that are connected to it go offline. So that's no good. So now we also have, through this extra piece of technology, also introduced by Mellanox, this thing called virtual function lag, the idea that we can actually bond together at the physical layer two physical devices and create a single virtual function from it. The combination of these things has brought about a system where we can have within VMs line rate performance and RDMA protocols combined with fault tolerance by combining two physical links together. And also to run this in a context where we can take a VM and move it from one machine to the next in a kind of like a checkpoint restart kind of way. But we can do it while the application is running. So we can do this live migration from one site to another. So the combination of these things, along with being able to provide strict security rules and firewall rules, is a transformative change that's happened recently within OpenStack networking. This is all on, I should say this is all on Ethernet hardware. There are Infiniband solutions in an OpenStack environment as well. So that is well covered too, but I don't think it has this kind of lag support within it. I think it's more multi-route. The way this works, I'll just quickly skip through it, is that when a packet comes through from one of our VMs, the VM's sitting down here, the first packet gets evaluated by the software rules within the hypervisor context. If it is considered to be a valid kind of flow, then it gets approved, and that will then bring it down into the kernel if it's too complex to implement in hardware, or it will actually implement the rules for this particular exchange within the hardware. And then you get flow rules so that after this we get zero impact, zero interruption from the hypervisor, and all of the traffic flows line rates. Now this is a useful thing. It's really based around an assumption that communication is based on conversations. So we will be communicating with a number of equivalents to queue pairs within our system. So it's not particularly good if you had a very large scale kind of all-to-all unidirectional message exchange, the kind of GUP style traffic. But there's about 25,000 of these flow rules, I believe, room for that many within the NIC. So I don't think that you could say it would work in, well, it works up to a very large scale anyway. So I think I'm quite happy with this. We get line rate bandwidth and a message latency of the order of about 2 microseconds using the lag offloading here. A bit higher than Rocky Ethernet by itself, but still very very powerful compared to a pure software-defined cloud. So I wanted to talk a little bit. I think I'll skip over this piece. It's probably a little bit too involved here, but I wanted to talk a little bit about how we use this. How we use this additional complexity and additional performance to good effect. And we had a case study working with a client in financial services who was looking to buy a very significant flash file system. But they wanted to evaluate the contenders, and they wanted to know whether it was how each of these worked at a medium level of scale. So in this case, we constructed a test environment based around multiple bonded 100 gigabit Ethernet links. And on one side of our network, we had a number of NVMe equipped file servers, bare metal file servers that were able to be deployed with various candidate storage technologies. Also connected to this network was our client test harness. In this case, it was an OpenStack test system with 5 hypervisors equipped with dual port bonded 100 gig. The hypervisors are using Cascade Lake services, so they're PCI Express Gen 3. So each of the hypervisors was capable on its PCI bus of about 100 gigabits, or 12.5 gigabytes a second. We instrumented this machine with the virtual function lag offloads, and then we generated 7 VM clients, each of them connected to a virtual function directly attached to the NICs. Assigned in a cyclical rotation, we built up our test load from one client's performance up to a full test configuration of about 35 clients. We were able to use this test harness then to evaluate 4 file systems in particular that were under consideration. Due to non-disclosure, I can't actually name the names, but I have got the graphs. So hopefully that's at least partly useful. We were using FIO, the Linux kernel IO benchmarking tool, and aggregating the data from 35 concurrent runs of FIO in order to provide useful graphs which showed us the performance overall. The kind of data that we get back is looking a bit like this. So along the x-axis is the number of clients in the configuration, and then we get the aggregation of up to 35 individual data sets. And so we get this nice sort of stacked rainbow graph. The thick red roof line is the combined performance of all systems. Just to keep the graphing a little bit simple, I've only plotted 2 things here. We do have fairly rich data from FIO, incredibly rich, really. But in this case, we're just looking at the IOPS for small reads, 4K reads in this case, and the bandwidth for large reads, so 1 megabyte reads in this case. So the first file system that we were testing against, we're looking at some interesting corners here. So we look at the peak sort of IOPS. We're looking at the overall scaling pattern of the graph as we go to more clients, so you can extrapolate a little bit. We're looking at this data point down here, the single client performance. So we're doing about 4 gigabytes a second with this file system. And then we're looking at the overall pattern of growth. And we go from 5 hypervisors, that's 1 VM on each hypervisor, to 10, where there's 2 VMs on each hypervisor, 15. So we're getting diminishing returns in terms of performance from each of our test hypervisors, up to about 38 gigabytes a second aggregate bandwidth across all of our clients. So that's not too bad. That's about 7.5 gigabytes a second for each of our hypervisors. Not too bad, but not as good as this one. So the second file system we looked at, we topped out at about 1 million IOPS, and we do appear to have hit a very strong roof line here on the graph here. So a nice knee of performance going up here. Performance for one client is still somewhat tepid, around 4 gigabytes a second, but we actually saturate all of the network interfaces on all of our hypervisors, peaking at 60 gigabytes a second here. But then we get this interesting kind of post-saturation sort of Hooke's law deformed region of the graph here. So we learn a couple of very useful features prototyping our file systems already, just at this sort of intermediate scale. Third file system we're looking at, the first 2 were using TCP, and this one is using RDMA. So we're using RDMA from our VMs, and we can see straight away that we're getting almost line rate performance from 1, 2, 3, 4, 5. So we get up to nearly saturating our 5 hypervisors simply from running 5 client VMs. We don't get quite as high a performance on aggregate, but we probably get better properties on this file system. It's not delivering half the IOPS of the file system B, but it's still obviously showing very good performance, particularly for single client levels of bandwidth. Fourth file system is not using TCP or RDMA, and it's using DPDK, the active polling technology, where we sort of bypass the kernel stack. And as a consequence of that, we get 2.5 million IOPS, where we were getting a best of about 1 million in the previous file systems. However, the bandwidth in this file system was somewhat shy of where we got to with the best on B and C. So I think this is an interesting experiment in order to show a range of different properties, and that all of these new storage technologies, there's still quite a bit of variety and diversity between them. While we were looking at file system performance, though, we did also measure local I/O performance. So the idea of caching data locally and using some node local storage, which does appear to be a strong factor in a lot of design decisions in the sort of co-design of exascale architectures. We built a machine with 7 NVMe devices raided together, and we could generate these graphs. I'm sorry, these are slightly different. So here we're looking at, on the left, a sort of a heat map histogram of I/O latency for different I/O sizes. We're getting about 200 microseconds I/O latency down into this NVMe array. So you can see the overhead of virtualization here. That's probably twice what you would expect for interacting with NVMe's direct. On the other hand, though, it does result in a VM that can generate about 22 gigabytes a second of I/O bandwidth into the VM through the file system generated on these NVMe interfaces. So we can saturate across a virtualization boundary 7 NVMe's concurrently. So there's anyone who says that VMs are no good at I/O, you can feel free to share this graph with them. I think, so it's an interesting question. I think this is our sort of miniature case study in how we can use a virtualized platform for rapid prototyping. And that actually shows very, very strong properties for quickly developing things and quickly producing test results and answers. In a virtualized case, I think HPC is still very much the black swan use case. HPC's patterns of usage and models of communicating still break all of the operating assumptions made in the design of cloud infrastructure, provisioning everything at once for one user with one image, everyone communicating at the same time in these kind of synchronous manners that DK was talking about. There's synchronized pathological worst case patterns in pretty much any direction you look. But I would say that this concept of bare metal cloud provides a sweet spot combining HPC performance with no overheads and most of the flexibility we get from cloud native interfaces. The combination of an optimized virtualized resource, such as the one the test case was done with, the case study, built on upon a substrate of performant bare metal, gives us also this additional thing of cloud native agility without any sacrifice of performance, and can quickly get us to the kind of answers that we might urgently be seeking. So I think probably that's all I've got time for today. But I wanted to thank a whole load of people for the infrastructure and some of the data that I used in this presentation. So thank you very much.
Thank you, Stig. Probably about 10 slides back, I think Joseph had made a comment / question here saying links bonded together have been around for a long time. So what's new?
What's new here is that we present one interface from those links into our VM, and that interface is RDMA capable. So I think the interesting piece here is that if we think of the left half of this box as being the guts of the hypervisor, we have these 200 gig links coming in, and out of the back of the NIC, we present a virtual function device, which is one device which represents both links. And that device looks like a Mellanox NIC in its own sense. So we can use it as a verbs target by itself. And it will generate rocky verbs traffic on the bonded link. And if one of the links goes down, it will go down the other one. And actually it will use them both in an active-active context. So we can generate on a machine that's capable, maybe a nice AMD EPYC node or something with PCIe Gen 4, we can generate, approaching sort of 170 gigabits a second of network bandwidth from one of these VMs going down a pair of active links here. and we can also use it as an RDMA device. So I think those are the key things. You're right, bonded links have been around since forever, but now we're able to use them in these new ways in a virtualized context as well.
Thank you. And Gabriel says, so DPDK has better IOPS than RDMA, but not better bandwidth. If yes, how is this explained?
Yeah, that's a surprise. It's got to go through the builds. So some of this will be down to the file system at the far end, I expect, so when we have DPDK active on this system, each of the VMs is dedicating a core to 100% polling within the system. And that is, for a VM, that's actually quite a big sacrifice, because I think the VMs that we were using as clients here were, they had 6 cores, I think, and they were CPU pinned to cores within the hypervisor. So they're fairly finely sliced. It might have been 8 cores, I'm not sure. But so actually, when we give up a core to DPDK, it has quite a big difference in terms of what we can do with it. But on the other hand, we have no interrupt latency anymore to worry about. So it is a trade-off. It's an interesting trade-off. I was expecting slightly more bandwidth out of this system than we got, but we're still at sort of 80% of the raw capacity of the network and the devices underneath it.
Great. Thank you, Stig. Stig Telfer, everyone. Appreciate the presentation.
Thank you very much.